All right, we're looking at section 4.7, which is on applied optimization. Optimization problems are basically word problems that involve coming up with a function and then finding its maximum or minimum value. Uh, this is probably one of the biggest applications of calculus. And what we're going to start with is sort of a classic example where you build a box by taking a flat sheet of metal or cardboard and you cut the corners out and build a box out of it. This is a classic problem. Pretty much any calculus book you find will have some version of this in it. So let's look at this. A box with an open top is to be constructed by cutting squares out of the corners of a piece of copper and folding the sides up. So let's just look at what's going on there. So we've got a square here of, in this case, copper. What we do is we cut corners out of it. And then we fold along these lines. So those four little squares are going to be wasted. But we take this, we fold along those lines, and we wind up getting a square box with no top. And it looks like this. All right, let's look at the dimensions. This was originally 3 by 3. And let's call each one of these lengths here x. So all these are little x by x squares. So when we fold this together and we get this box, what we have is a box with a length and a width of 3 minus 2x. And the height of the thing from top to bottom is x, because that comes from the x over there. So what we want to do is maximize the volume of this box. Now, before we do that, I want to talk about the wrong way to do this. There's going to be some x that's the best. We don't want x to be too small. If x is really small, then we wind up getting something that's really just a flat sheet, or maybe a flat sheet with a tiny lip on the side, like a cookie sheet or something, and that's not going to have much volume in it. The other extreme thing is if we make x really big, then we're going to cut it away. We're going to have a really large x here, and we're going to have the really tall, basically a square drinking straw or something. And that's not going to have much volume in it either. So somewhere in the middle is going to be a good value to use for x. Let's see, the volume is going to be 3 minus 2x squared times x. And if we look at x, x needs to be between 0 and 3/2. Why? Well, you can't have a negative length. If we had 0 length, then it's just the thing's going to have 0 volume. It's just the flat square. And the 3/2 comes from, if we cut x off of one side and x off of the other, then the most we could do is go to the middle, which is going to be halfway across, so 3/2. So what we need to do is maximize this function. All right, so first let's multiply it out. Volume is going to be, let's see, if you square that out, you get square the first, multiply the two things together and double it, then square the last. So my volume is going to be, I'm going to distribute that x through there, but I'm also going to change the order. I'm going to put them in decreasing order. So you get 4x cubed minus 12x squared plus 9x. And I want to take the derivative of that and find its critical numbers. Because basically what we're doing now is we're finding the absolute max of this function on this interval here. So the derivative is going to be 12x squared minus 24x plus 9. So you got to set that equal to 0 and solve. Now, first thing I would do is divide everything by 3, and I get 4x squared minus 8x plus 3. And can I factor that? Maybe. I'm going to be stubborn and try to factor it. If you don't see how to factor it immediately, you can always just use the quadratic formula. Let's see, if I factor this as 2x and 2x, and the 3 is 3 and 1, I think that'll work, because this will give me 6x and 2x, and yet those will add up to 8. So if I make both of these minus, this gives me 2x minus 1 is 0, so x is 1/2. And this gives me 2x is 3, so x is 3/2. So I've got two critical numbers here to look at. And are they both in the interval? Yeah, one of them's right on the end of it, but they're both there. So I'm going to treat this like an absolute max-min problem. Let's look at f, or not f. In this case, we're calling it v. v of x, for the various values of x we've got here. Our endpoint, 1/2, and our other endpoint, which is also a critical number. Two of these are really easy to work out. If v is 0, now keep in mind, you can plug into here for v, or you can plug into here for v, either one. And this one up here is going to be easier to deal with because you plug 0 in, you're just going to get 0. Likewise, if you plug in 3/2, the 3 minus 2 times x, that's going to give you 0 there as well. And finally, if you plug in 1/2, you get, again, you can plug it into here or here. I'm going to plug into there because it's going to be easier. Plug in 1/2, you get 3 minus 2 times 1/2 squared times 1/2. Let's see, what is that? 3 minus 1 is 2 squared times 1/2 is 2. Let me just double check that. 3 minus 1, no, that's, yeah. 3 minus 1 is 2, squared is 4, times 1/2 is 2. So yeah, it looks like that's my, my maximum volume, and that's going to happen at 1/2. So let's see what was asked. What is the maximum volume possible? The answer to that is 2 cubic feet. All right. Now, if you look at this next page, there's sort of a set of guidelines for solving an optimization problem. And I want to just go through those quickly. Read the problem, of course. Draw a picture if necessary. Introduce some variables and determine the quantity that's got to be maximized or minimized. Express Q in terms of the other variable. That was pretty easy on this one. We only had one variable to deal with, x. And so volume, we express that in terms of the other variables. Let's see. If Q is a function of more than one variable, eliminate all of them but one. That way you can take the derivative of it with respect to that variable. Then find the maximum or minimum value of Q and then answer the question. This down here is an important step because sometimes the question will ask you different things. Sometimes it will say, what's the maximum volume or what's the minimum volume? Sometimes it might ask you, what are the dimensions that give you the maximum volume? Or something like that. So just, don't get to the end of the problem and say, okay, there's my maximum value, I'm done. Make sure you answer whatever the problem's actually asking you for. Now, I want to do several more examples, but these tend to be somewhat long. So what I'm going to do is go through the rest of these, probably mostly one per video. I might do the next couple in a single video. But anyway, that's it for now.